A modern airliner could be engineered to fly far faster than it does, yet every one of them holds at roughly 560 miles per hour through the air and refuses to go past it. We crossed the sound barrier in a fighter jet in 1947. We flew paying passengers faster than a rifle bullet in the 1970s. So why, decades later, is the jet you'll board this year slower than one your grandparents could have flown? But this isn't a failure of engineering. So what is actually holding every airliner below that line? The answer involves a wall of drag that appears out of nowhere, a fuel bill that makes the math absurd, a 50-year-old ban written into law, and an industry that decided for half a century that faster simply wasn't worth it until now. Passengers looking at seatback screens or online flight trackers often see speeds exceeding 700 or even 800 miles per hour. This number represents ground speed, the velocity of the aircraft relative to the Earth's surface. It is entirely separate from true airspeed, which measures the actual rate of travel through the surrounding air. To understand how this works, imagine a person walking forward inside a moving train. To an observer standing on the platform, the walker travels at the speed of their steps combined with the speed of the train. In the upper atmosphere, a powerful wind like the jet stream acts as that moving train. When a standard jetliner encounters a 150 miles per hour tailwind, the ground speed climbs past 700 miles per hour, even though the true airspeed remains at a standard 560 miles per hour. The airframe experiences no extra stress and remains safely subsonic. If wind alone accounts for these high flight tracker numbers, what physical forces set the limit when an aircraft tries to push faster through the air? To find the real ceiling of commercial flight, the focus must shift from ground speed to true airspeed, the velocity of the aircraft relative only to the air mass it penetrates. Modern wide-body airliners, such as the Boeing 787 or Airbus A350, are designed to cruise at approximately Mach 0.85. At a standard cruise altitude of 35,000 feet, the ambient temperature drops to minus 54 degrees Celsius. Under these conditions, the speed of sound is roughly 660 miles per hour. Cruising at Mach 0.85 therefore translates to a true airspeed of about 560 miles per hour, meaning the aircraft remains safely subsonic. This relationship reveals that the 800 miles per hour limit is a highly deliberate engineering boundary. The true mystery centers on why commercial transports do not fly supersonic relative to the surrounding air, rather than how high winds temporarily inflate the numbers on a passenger screen. Why has the global aviation industry spent more than half a century holding this precise subsonic line? A wing generates lift by forcing airflow to accelerate over its curved upper surface. Because of this geometry, the air traveling over the top of the wing moves significantly faster than the aircraft itself. When a modern transport jet cruises at a speed of Mach 0.8, the accelerated air moving over the wing can easily reach Mach 1. This mixed state marks the beginning of the transonic regime, referred to in Spanish as el régimen transónico, where subsonic and supersonic airflows exist simultaneously on the same structure. To visualize this process, imagine a boat moving through a river. Even if the boat travels at a moderate speed, the water must squeeze and accelerate around the curved sides of the hull, moving much faster relative to the boat. On an aircraft, when this local airspeed reaches the speed of sound, a normal shockwave forms on the upper surface. This shockwave creates a sudden pressure jump and thickens the boundary layer of air, causing a massive sudden spike in wave drag. The wing encounters supersonic physics long before the cabin does. How do aerodynamicists shape modern wings to delay this shockwave and manage the resulting drag? Inside this transonic region, the normal shockwave behaves like a physical obstacle on the wing. As air passes through this boundary, its pressure and density jump instantly, disrupting the smooth airflow downstream. This disruption causes the boundary layer to detach from the surface, creating a highly turbulent wake behind the shock. This aerodynamic penalty triggers a phenomenon known as drag divergence. It represents the specific point where the wing's drag coefficient begins to climb exponentially rather than linearly. To visualize this, consider pushing a wide shovel through loose sand. At slow speeds, the sand slides off the blade with little resistance. Push faster, and the sand abruptly packs into a solid, heavy wall directly in front of you, demanding vastly more effort for every inch of forward progress. Once a passenger jet passes its drag divergence Mach number, typically between Mach 0.8 and 0.88, the engine thrust required to fly just a few miles per hour faster increases exponentially. Aerodynamic resistance quickly consumes any efficiency gains, forcing the power plants to work substantially harder to achieve diminishing returns. Pushing through this resistance is physically possible, but it requires brute force. If drag rises so sharply, why not simply build larger engines to punch through the barrier? The answer to that question is not a matter of raw engineering speculation. Commercial aviation already answered the feasibility question decades ago. On January 21, 1976, the Anglo-French Concorde entered scheduled passenger service, proving that sustained supersonic flight was not a theoretical dream, but a daily operational reality. For 27 years, this slender delta-wing transport crossed the Atlantic at Mach 2.04, approximately 1,350 miles per hour. Flying at twice the speed of sound, Concorde carried over 2.5 million passengers at altitudes up to 60,000 feet, effectively cutting transatlantic travel times in half. It operated as a highly exclusive premium service, turning the engineering challenge of wave drag into a routine 3.5-hour flight between London and New York. But Concorde was not a template for the mass market. It was an elite proof of concept. While its 27-year run established that bypassing the transonic barrier was technically achievable, it did not prove that such speeds could be sustained under standard airline economics. When the fleet was retired in October 2003, it left behind a stark lesson about the true cost of speed. If engineering could master the physics of Mach 2, why did the rest of the aviation industry refuse to follow? Modern commercial aviation operates on a razor-thin margin, where fuel consumption directly dictates profitability. For a twin-engine wide-body like the Boeing 787 or Airbus A350 cruising at Mach 0.85, roughly 560 miles per hour, true airspeed represents a highly optimized equilibrium. At this speed, the high-bypass turbofans operate at their peak thermal efficiency, and the swept-wing airframe experiences a stable, predictable level of drag. To understand why airlines refuse to push past this boundary, consider the physical cost of speed. Below the drag divergence Mach number, aerodynamic resistance increases predictably. But once an aircraft attempts to edge past Mach 0.85, the drag curve spikes exponentially. It is the aerodynamic equivalent of trying to sprint neck-deep in water. A small increase in forward speed requires a massive, exhausting expenditure of energy. To fly just 10% faster, a passenger jet must burn up to 50% more fuel. High-bypass turbofans are optimized precisely for this subsonic sweet spot, and forcing them out of it destroys their efficiency. For airline dispatchers and fleet planners, this physical reality forces a harsh financial trade-off. On a standard 3,500-mile transatlantic route, pushing an aircraft to its absolute aerodynamic limit might shave 30 minutes off a 7-hour flight. Yet those 30 minutes saved would require burning thousands of gallons of additional fuel, completely erasing the flight's commercial profit margin. The industry recognized early on that speed alone does not create value if the market cannot absorb the operating deficit. The global aviation network was not built to be a high-speed racing system, but a highly disciplined mass transit utility. Efficiency, not speed, is the ultimate metric of commercial success. Even if an airline solved the physics of transonic drag and absorbed the brutal fuel costs, they would still run headfirst into a wall that had nothing to do with engineering. This is the part that catches people off guard. The speed limit is not a result of pilot reluctance or operational caution. It is a matter of federal law. In 1973, the Federal Aviation Administration, the FAA, codified 14 CFR, Section 91.817, imposing a strict ban on civil supersonic flight over land. The issue was the sonic boom, an inescapable physical phenomenon where an aircraft traveling faster than sound creates a continuous cone of compressed air behind it. To those on the ground, This pressure wave hits like an explosive thunderclap. This legal barrier was forged by intense public backlash. In 1964, the FAA conducted Operation Bongo 2, blasting Oklahoma City with 1,253 sonic booms over a 6-month period. The resulting reports of cracked plaster, broken dishes, and terrified livestock galvanized public opposition. An aircraft fully capable of Mach 2 was now legally blocked from its fastest overland profile. The ceiling was no longer just a barrier of physics and finance, it was a matter of law. With physics, economics, and law forming an absolute 3-part lock, the subsonic ceiling of passenger flight became permanent. Before analyzing the exact balance sheets that cemented this industry-wide compromise, consider supporting these deep dive analyses. If you value technically precise reconstructions of engineering history, please take a moment to like this video. You can also share your thoughts in the comments on whether this triple barrier will ever be broken. How do these invisible forces change your perspective on modern air travel? The next step is to examine the financial calculations that finalize the airline verdict. Every route in an airline network must survive a strict multivariable ledger. When planners calculate the feasibility of higher speeds, they weigh a handful of saved minutes against a compounding cascade of expenses. On a typical 3,000-mile route, saving 30 minutes by flying closer to the speed of sound requires burning thousands of gallons of extra fuel. But fuel is only the first entry on the balance sheet. Operating near the transonic boundary accelerates engine wear, escalating the maintenance burden. It demands heavier, more expensive airframes and restricts routing options due to noise regulations. For 50 years, fleet planners ran these exact numbers, and the equation never balanced in favor of speed. The Concorde served as the ultimate proof that mastering the engineering of high speed is entirely separate from building a sustainable commercial business. Without a broad market of passengers willing to pay 5-figure ticket prices, the math collapses. Ultimately, the subsonic limit is not a failure of imagination. It is a triumph of balance sheet discipline. Today, the 50-year subsonic lock faces its first active challenge. On January 28, 2025, Boom Supersonic's XB-1 demonstrator reportedly reached Mach 1.122. That milestone precedes its scheduled retirement, though this operational status requires final verification. On the regulatory front, claims of an executive order rolling back the 1973 overland supersonic flight ban also await official confirmation. To codify these policy changes, legislative efforts are moving through Congress. The proposed Supersonic Aviation Modernization Act seeks to grant the Federal Aviation Administration authority to establish performance-based, low-boom noise standards, replacing the absolute speed limit with a modern, audible noise ceiling. These administrative and legislative maneuvers suggest that the technical, financial, and legal boundaries that defined commercial flight for decades are no longer entirely secure. The subsonic compromise is now being actively renegotiated in real time. To follow the evolution of these high-speed systems, please subscribe. Designing a modern supersonic transport means replacing Concorde's brute force approach with targeted aerodynamics. The NASA X-59 tests this shift through precise airframe shaping, redirecting shockwaves upward to prevent them from merging into a loud double boom. This low boom design, combined with Mach cutoff flight profiles, where the ground temperature naturally deflects sound waves, aims to turn an explosive thunderclap into a soft, distant thump. It is the acoustic difference between slamming a door and gently clicking a latch. For commercial routes, Boom Supersonic is applying these principles to the Overture. Designed to carry 64 to 80 passengers at Mach 1.7, the aircraft relies on lightweight carbon composites, digital stability systems, and a dedicated afterburner-free power plant called the Symphony engine, built to run entirely on sustainable aviation fuel. Yet, while quiet airframes can legally unlock overland routes, they do not bypass basic thermodynamics. Pushing through the transonic boundary still demands a steep energy premium, meaning the route economics remain tied to high-value business travel. If technology can finally quiet the boom, will the flying public pay the premium to cross the sound barrier? airlines maintain a cautious stance driven by historical realism, rather than operational timidity. The earlier supersonic era left lasting financial scars, establishing a hard lesson that passenger flight at twice the speed of sound remains a fragile, premium niche. Today, fleet planners and executives analyze these new programs through the lens of institutional memory, examining every projection with healthy skepticism. They must determine if lightweight carbon composites and quiet boom designs can fundamentally rewrite the business model, resolving the permanent tension between what engineering can achieve and what the market will actually support. This makes the modern push for speed an unresolved commercial experiment rather than a guaranteed comeback. Ultimately, aviation companies are evaluating whether these new systems can transcend the thermodynamic penalties that grounded their predecessors, or if passenger flight will remain firmly anchored at subsonic speeds. Subscribe to follow the future of flight. Today, the half-century speed compromise is finally shifting. As low-boom technology enters active flight testing, aviation stands on the threshold of a new era. Yet the underlying tension remains. The future of commercial flight will not be decided by how fast aircraft can fly, but by how efficiently they can navigate the realities of physics and economics and law. Subscribe for more in-depth engineering analysis.